Hi, I'm Prof. Joe. I'm a professor for automation and measurement technology at the University of Kempten in the very south of Bavaria. And this is part 2 of chapter 2 of my lecture Measurement Technology at the University of Applied Sciences in Kempten. As you all know, this lecture is AI accompanied, so down below there's a link to a prepared GPT which contains all the facts, the content and the stuff you need to learn. And in these videos, I'm willing to give you focus, explanations, descriptions, and explain some difficulties and give you context around the real hard facts within the GPT. So today we will talk about error definitions, meaning how we get errors using measurement devices. So normally you buy a measurement device. You get a data sheet along with that, and in that data sheet, the maximum errors possible with that measurement device are described. We can get those maximum errors. So, as you remember, we never know about the actual real value, but we have our standards for our units. So those unit standards are somehow our real well-defined quantities. That's the point we humans take to have as a certain value for a certain time or distance or whatsoever. So, assuming that somebody building a measurement device is able to define somewhat the maximal error which can be made using his measurement device. So, having said that, there are different ways people describe that. One way is the class of a measurement device, which for example is 1 or which is 0.1. And that class is more or less defined by the maximal error, the maximal possible error divided by the maximal value the measurement device can measure actually. So, and now that means having a measurement device with class 1, this error here is about or below 1%. The 1 means 1%. So measurement device having class 0.1 is a better device because this error then is below 1.0%. That's something which you will see at the rough descriptions of your measurement device when buying it. Not always, but sometimes. And so you now have the idea how to interpret what a class 1 measurement device would be. More common within the data sheets of the measurement device are different descriptions. Something like you have a maximum error of, for example, plus minus 1% of the displayed value plus 2 digits. So that's well defined. The displayed value, it's easy to know, just read the display. But sometimes those digits or the name digits is a little bit unknown, and just explaining it roughly, that means when you have a display of 0.5, for example, a digit would be a change in the last place over here. So changing from 5 to 6, we get a digit of the size 0.001. Getting that error is easy, having a data sheet giving you that information. You take your measurement, you read your data sheet, and you calculate your error. So you can have, in the end, your measurement plus minus the maximum error. That's our goal. And by having those definitions in the data sheets, we are able to have those definitions. this is defined by the guy or the people which built the measurement device, and we have to trust them somehow. Perhaps we will get into the situation we are building some measurement device on our own, and so there are different influences which may be part of such a definition for a maximum error. Some of those influences may be quantization, meaning normally you have an analog digital converter that has some resolution, for example 12 bits, and so you have some quantization error which gives you most of the time those digits at that place over here. Moreover, you have some dynamic behavior of your measurement device. You know it and you say the readings should be taken after 1 second, but you know there may be fluctuations after 10 to 20 seconds. You know about those fluctuations because you know your self-built measurement device very well. So you just add some percentage of the displayed value to cope with those fluctuations. Moreover, for example, you know your measurement device behaves differently. For large currents will heat up your measurement device and by that change your measurement. A low current won't. So there may be differences also. What we do with that is pack it into the datasheet, or when it's not about building a measurement device for other people, pack it into your error descriptions. Try to cope with it. Try to at least define a maximum error which is really maximal, which has a certain amount of error which makes sure every measurement will be in this range. So add up 10% to any error you can calculate, for example, to be sure the given error is a realistic one. Okay, so those error definitions are fine, and at that point we have solved the problem of part 1, the problem of not knowing our measurement quantity. Now we just know our error, and now in that equation we can have a glimpse for our measurement quantity over here. So this aim and focus is well defined, and now we can work with those errors, having in mind that our maximum errors are derived from datasheets or given by the measurement device producer, giving us as much information as possible. So looking into those datasheets, don't hesitate to look through the whole thing, not only looking on the first page, because perhaps on page 3 there's some comment about measuring high currents, which says you should wait 1 minute between each measurement, and so on and so on. And that may have influence for your error too. So always, when using a measurement device, try to use it as correctly as possible by really knowing the datasheet. That's perhaps the most important thing to know about those error definitions. Because written down as an equation, it's nothing complicated or difficult about that stuff. But it's the most difficult part about it is using it correctly, using it as the datasheet describes to you. Talking about the maximum error, there are some additional definitions one can make about the error types. So we have already talked about in part 1 influences which we don't cope and influences which we know from the outside for our measurement device. And so we will systematically somehow define those. So there are the systematic errors. And to say it in short, they are just known. We know everything about it. We know the quantity, we know the time when they occur, and we know how to correct them. And that's the thing we have to do with those. So, for example, the influence of the temperature for a measurement device given in your datasheet should be corrected. A more better example, which we will treat in chapter 5 presumably, is about the internal resistance of your voltage measurement device, for example, because that internal resistance changes your whole setup. But we know about that resistance, so we can correct it. Easy. Then there are unknown systematic errors. Those are known in part. And we don't know how to cope with them primarily. Meaning, yeah, we know about the magnetic field of the Earth, but should we treat it or should we ignore it? There is an influence, but we don't know how to deal with it. The easiest way to deal with those when you don't know what to do is increase the errors. That's the easiest way to cope with those. I don't know about it, but I presumably can have an idea of how big that influence is. Imagine a measurement device for a magnetic field. You know about the magnetic field of the Earth, so just take the maximum magnetic field of the Earth and add it to your error. That might be the easiest way to think about it, but you will be for sure correct with your error definitions and with the stuff you tell to the person you're giving your measurements to. Then finally, there are random errors. They're completely unknown. So, those random errors have one advantage. They're random. Whenever something is random, we can do statistics. And that's how we can treat those. So, for example, calculating a mean value, calculating a standard deviation. That's statistical treating of random errors. The nice thing about randomness is the randomness, so we have some methods to cope with those errors at all. So you see, we have some things we can do about all errors. So the most important thing perhaps is that one, that whenever you know something about an error, or better said, whenever you know the error, correct it. Sounds stupid, but sometimes we feel lazy. I know there's an internal resistance of my voltage measurement device, but oh man, that's complicated to correct it. I'm not into it, no, and it's so small, nobody would recognize when I'm just ignoring it, and that makes my outcome really lazy, so I can chill around a little bit. You know where I'm aiming at. It's something you have to do when you're able to do, so correct your errors whenever possible. Now, those unknown systematic errors, it's great to think about them. So it's at that point you are talking about, I stay with my example. Whenever you start to talk about the magnetic field of the Earth influencing your measurement, you're within a very good position because you really emphasize the treatment of your errors. For sure, whenever you start to think about the magnetic field of the Earth as an error source, you already have coped with all those systematic errors you can correct. So that's a really nice to have, but it's not a must. Then in the end, those random errors, that's something we can do with any measurement. We can have any measurement taken 2 times, 3 times, 4 times, 5 times, 10 times, and so on. And so we always have the possibility to somehow enlarge, to enrich our measurements by doing some statistics. But we'll see more facts about that stuff in chapter 3. yeah, summing all up, there are different error influences. We already heard about them in part 1, and we have now the possibility to explain, to get a real value for the error, for the maximum error of a measurement device. And having that standpoint, the next question is how to work with those erroneous values, with those measurement values having an error. Because using those in an equation will have an influence on the equation. That's about what I'm talking in part 3 when we are talking about error propagation. So if you like that stuff, don't hesitate, subscribe and have fun doing measurement technology. See you next time.